Welcome to Engineering Studio with Dr. Mohammed Tahir. We are going through the revision of some basic concepts. In this video, we will start from the bending. So what is bending? Or what happens when bending occur in a structural beams? If we apply a load on a simply supported beam, it will deflect in downward direction, it will bend, and the top fibers will compress and the bottom fiber will elongate. So there will be elongation on one surface and the shortening on the other surface. The surface where compression occurs, the fiber will shorten, and the surface where the tension occurs, the fibers will elongate. But there is a plane at the center which is unchanged. So that plane is termed as neutral plane or neutral axis. So in case of bending of beam, the plane section remain plane and perpendicular to the normal and perpendicular to the neutral axis. So we can demonstrate this with the help of a model. So here we have a beam and we have marked the neutral plane as well as the vertical section. So if we bend it, so at bottom there will be compression and the fibers will be shortened, and at the top there will be tension and the fibers will be elongate. And this neutral axis will remain unchanged. And here the sections are straight, so sections are plane. There is no distortion on the section. Similarly, these sections are perpendicular to the neutral axis. So this assumption or this phenomena is used to develop the relation for stresses which are developed during the bending. Sigma is equal to my over I, flexural stresses. So the normal stress on a cross section of a beam is distributed linearly with the maximum normal stress occurring on a surface farthest from the neutral plane. So when a beam is subjected to bending, so the normal stress is perpendicular to the applied load, or we can say perpendicular to the section, will occur, and the magnitude of or the variation of these stresses is linear. So zero at the neutral axis and maximum at the extreme fiber. At the extreme fiber, at the top compression and at the bottom tension. So here it is compression and here it is tension. We can also draw it like this. Here it is compression, forces toward the section, and here it is tension. And their extreme value or the highest value is at the extreme fibers. And we can calculate the stress at any location by using this relation. Sigma is equal to mc or my over I. Here the c is distance from the neutral axis up to the point where we want to calculate the stress value. So here there is a demonstration of bending phenomena, how the bending occurs and how it affects the design. For the model demonstration, we have selected a stapler. So the question is how the staples of stapler are bent inside the stapler. So we apply the load over here, and the needles come in contact at this position, and because of this inclined surface, when the needle comes over here and there is a pressure on the top, here act two forces, horizontal as well as vertical. Vertical force as well as horizontal force. And this vertical force initially try to bend this part of needle. And the bending will occur at the farthest point because of this horizontal load, the bending moment will be maximum at the farthest point. So the bending will occur at this corner. So a small, because of this horizontal force, this part of the needle will bend in this direction, and this horizontal force will disappear. Now the next bending will be because of this vertical force, and here the bending moment will be because of this eccentricity between the applied force as well as the point of rotation. So when we keep on increasing the force or applying the force at the top, so this vertical force or the vertical component of the reaction will keep on bending this part of needle, and ultimately we will have this shape. So from this model we can conclude that the bending moment will be larger at the farthest point, and the failure or the bending will occur at the point where the bending moment is maximum. So similarly, if we see in this bench, a concrete bench, here we have a failure at this point. Although we have a higher depth at this section, but again the failure is at this point. It is because that this cantilever portion have maximum bending moment at this location. So this will be its critical point for the design. These figures show the demonstration how the concept of bending is utilized. The removal of material from the section close to neutral axis where flexural stress is less. So to resist the bending, we can remove the material near to the neutral axis. This is because the stiffness or the flexural stiffness of the member is dependent on the second moment of area, and the second moment of area will not change if we remove the material close to the neutral axis. If we keep on increasing the distance of the material from the neutral axis, the stiffness of the section will increase. Similarly, this second figure shows that we can reduce the depth of the section where the bending moment is less. At the supports here, the bending moment is 0, so we can reduce the depth, and as the bending moment keep on increasing near to the center, so we can keep the material away from the neutral axis. And on tension side, for steels, we can use the smaller section, the smaller cables, and in case of portion where the compression occurs, we need a larger section to avoid the buckling as well as instability due to local buckling. So this figure shows how we can reduce the bending moment in structures. So if we can reduce the bending moment somehow, the required section, the depth of required section will be reduced. So if our structure has simple supports, so the maximum bending moment will be WL square by 8 at the center. But if we have a beam with fixed end, in that case the maximum bending moment will be at the support, which is WL square over 12, and at the center the moment will be WL square over 24. So just by changing the end conditions, we have reduced the middle bending moment, which is WL square over 8. We have reduced it from WL square over 8 to WL square over 24. And again the bending moment at the support, which is WL square over 12, it is less than WL square over 8. So if we change the condition from simply supported to fixed ended, the required section will reduce. We will design this, or we will decide the depth based on the reduced bending moment. So if we see this figure here, these internal supports, at these internal supports we have a continuous beam, this continuous beam. So for the interior span we will consider it as a fixed ended, and as a result the bending moment will be maximum WL square over 12. But in case of this end span, if we do not provide this overhang, this exterior support will be a simple support. So because of this simple support, the moment at the center will increase. So when this moment at the center will increase, so we need to increase its depth. So to avoid that, to keep the depth same as that of the interior panel, we can change this support condition. So we can make it as continuous. We can make it as continuous by extending this beam and adding some overhangs. And we have applied this force in this direction at the end of the overhang, and this will make this internal support as a continuous beam. So by just changing the end condition, we have reduced the bending moment. As a result, the required section will be less. The next concept is shear, a force which tends to slide the material on one side of the surface relative to the material on the other side of the surface in the direction parallel to the surface is termed as shear force. So if we have two surfaces like this, one above the other, and we apply a force over here, a resistive force over here, so this force will try to slide this upper surface over the lower surface. So this type of force is termed as shear force, and the resistance between these two surfaces will be termed as shear resistance. If there is no resistance between these two surfaces, so we can easily move the upper surface over the lower surface. We can slide this upper surface over the lower surface. So here we have our demonstration. If we take two books, and in one book we punch holes and insert bolts to restrict the movement between the pages, and in the second case we do not provide any bolt and the pages are free to slide over each other. In that case, if we support these books at the ends like this, at here and here, and we apply force at this corner. So in first case, where we have provided the bolts, under the application of load there will be no slide between the pages. But here in the second case, just with a small force, the pages will slide over each other and they will move relative to each other. So here we have shear resistance, but here in this case we do not have shear resistance, and the force that we have applied have caused the sliding between the pages. So this type of force is termed as shear force, and the resistance provided by these bolts is the shear resistance. So next, how this shear resistance affect the flexural stiffness of beams. So for example, for the previous model, the model of book, in one case we have inserted the bolt to improve the shear resistance, and in the second case we have not inserted the bolts, and the shear resistance between the pages is almost zero. And if we consider it as a beam and apply the load, in the first case when we have inserted the bolts, there will be very small deflection. So this is because these shear resistance have improved the flexural capacity of the beam. But in the second case, where these pages are free to slide over each other, the stiffness of the beam will be significantly less, and as a result the beam will deflect. We can also see some other model. Here we have two wooden plates, and if we place it one over the other and try to bend, so we can bend it easily. So excessive bending just with the help of hand. But if we join these two plates with the help of bolts and we restrict their movement relative to each other, so in that case if we try to bend, so it will not be possible to bend it, or there will be very small bending in that case. So this is because by providing the shear resistance between the two surfaces, the stiffness of the section or the stiffness of the beam will significantly improve. Okay, where we can use this concept of shear resistance. If we want to strengthen a beam with the help of steel plates, and we need to add multiple plates, and if we do not add the shear stiffeners or the bolts to hold these plates together and to provide the shear resistance between these plates, then the stiffness of the beam will not improve significantly. But if we add these bolts between these plates, the shear resistance between these plates will increase significantly, and as a result the stiffness of the beam will increase. and we can increase its flexural strength. In the second case, we have a shock absorber of vehicles. So in that case, we do not provide the bolts between the plates. This is because in case of shock absorber, we need to limit the flexural stiffness of the beam to accommodate the shocks, to absorb the shocks. If we provide bolts over here, so in that case, the stiffness of this shock absorber will increase significantly, and the purpose for which it is designed, it will not be fulfilled. Okay, the next concept is torsion, a moment that is applied about the longitudinal axis. In case of bending, we apply the moment about the transverse axis, about this horizontal axis, which is, we can say, y. So this is if it is x, and this is y and z. So this is in case of bending, the moment is applied about this y or z axis, perpendicular to the longitudinal axis. But in case of torsion, we apply the moment about the longitudinal axis, about this axis x of the member, and this moment is termed as torque, and this moment tend to twist the member. So it will twist like this about the axis, about the longitudinal axis, and this phenomena is termed as torsion. So twisting about the longitudinal axis is termed as torsion. Okay, to resist the torsion, which type of section are good and which type of section are not good? So for a circular shaft or closed circular section, the plane circular section remain plane, and the cross section at the end of the member remain flat. So here we can see the circular section remain plane, and the end section is again plane, and the length and the radius of the member will not change. So if the member is circular shaft or closed circular section, just applying the torque, by applying the torque, there will be no change in its length as well as radius. So plane circular section remain perpendicular to the longitudinal axis. So these assumptions, just like in case of bending, the plane section remain plane and perpendicular to the neutral axis. The similar assumptions or similar phenomena occur in case of circular shaft as well as closed circular sections. There is no distortion in the section. But in case of non-circular section or open section, so when we apply the torsion, there will exist wrapping. The cross section will turn into zigzag shape, into distorted shapes, which is termed as wrapping, as well as the radius and the length of the member will change. So there will be unequal deformation in the fibers of the member. The question is, why this happen? Why in case of open section there is distortion in the member or the twist in the member? So this is because the phenomena of shear flow. So torsional stiffness of open section is significantly less than that of closed section due to reversal of shear flow in case of open section. So here the shear flow will be like this, and then in this direction, in this direction. And at the end, again it will turn back. So at any section, if we cut a section over here the stresses in the wall will be like this, just like the flexural stresses. On one side there will be compression, and on the other side there will be tension, and at the center there will be some material where the stresses is zero. So as a result, the full thickness of the member will not be utilized, the full material strength will not be utilized to resist the shear forces or the shear or the torsion. As a result, because of this distribution of stresses, the member will buckle locally, as well as there will be distortion in the section, and the full strength of the material will not be utilized. As a result, just at a small torque, the member can be twisted or member can be sheared. But in case of closed section, the shear flow will be like this. It will be in one direction, and at any section, if we cut a section at any point, so the distribution will be like this. The full strength of the member will be utilized to resist the torsion. So that's why if we design a member for torsion, so in that case the best selection will be a circular shaft, solid section, circular hollow section. Closed section is also a good option. If it is not a circular, then it should be a solid section or closed section. But C section, angle sections, these are not the good option for a member which is subjected to torsion. We need to avoid this type of section for torsional members. So here we have a model demonstration that if we take two rods or two sections, hollow sections, in the first case it is open section, and in the second case it is a closed section, and we apply a torque on that section. So the first section will twist easily just with the help of hand, but in case of second section, where the section is a closed section, so it will not be easy to twist such a section. So this is because in case of closed section, the torsional stiffness is significantly high. Okay, if we are supposed to use some open section like C section, then it is necessary to apply the load at the shear center. If the applied load is passing through the shear center of the member, then there will be no torsion, and if it is acting away from the shear center, then there will occur torsion in that member. So for that we have a model demonstration. We have three beams, cantilever beams made up of channel section, and in the first case the load is acting away from the shear center, so because of that load there is bending as well as twisting in the member. In the second case, the load is passing through the shear center of this section, so here only we will have bending in downward direction, there will be no torsion. And in third case, if the again load is acting away from the shear center, so there will be bending as well as torsion in that member. So if we want to avoid the torsion in the section, so we need to apply the load at the shear centers. So that is why when we are going to design the purlin in case of truss roof system, we use Z section, because here the load will pass from the shear center of this section. But if we use C section, in this case the load will pass from here, so it is away from the shear center, so in that case there will be twisting in the member. So here we have a practical application of this concept. To avoid the torsion in case of bridge decks, box girder, we use box girders, because in case of bridges, the load of vehicle can act on any side of the deck slab. For example, load is acting over here, and if we have a beam or the girder at the center, so because of that load there will be a torsion or twisting inside this girder. So to resist that torsion, we provide these hollow sections, box girder. So this is a closed section, so this can resist the torsion very effectively. Okay, next is the concept of stress. So stress is the load acting per unit area of a surface. So load per unit area is termed as stress. For a given external or internal forces, the smaller the area of the member resisting the force, higher will be the stress. So in this case, we have a balloon and it is placed on a single nail. So in that case, the resistive area is very small. So just under the application of very small load, so this will fail. The stress will reach its failure stress. But if we increase the contact area, the resistive area, by placing it on multiple nails, in that case it can resist the higher amount of load. Similarly, the demonstration over here, if we try to sleep on a single nail, it is impossible. But if we place a multiple nails in this, just like this, and if we lay down on that nails, so in that case it will be possible, because in that case the contact area is large because of the multiple nails, and the stress acting on the body will be less, and no nail will penetrate in our body. So larger the stress, larger will be the deformation. So here we have a demonstration for this concept. Here we have a foam and we have applied the load or applied the stress, but the contact area is large. So in that case deformation will be less. In the second case, the contact area is small, so there is huge deformation because of this small area. So this is because when the area is small, stress is large, and because of larger stress, deformation will be more. The next concept is span and deflection. For a uniformly distributed load, the deflection of a beam is proportional to the span to the power 4, and for concentrated load it is span to the power 3. So just by increasing the span by 2 times, the deflection will increase 16 times if uniformly distributed load is acting on that beam. Okay, to reduce the deflection, an increase in depth of a beam is more effective than increase in its width. So here we have a demonstration that just we have increased the span and the deflection has significantly increased. And if we want to improve the stiffness of the member, or we want to reduce the deflection, so then the better option is to increase its depth instead of width. Here we have a same section and same span, but here the depth is less but the width is large. Here we have reduced the width but increased the depth. In that case there will be very less deflection. So this is the same concept as we have discussed earlier in case of second moment of area. When the width is larger and the depth is small, so the second moment of area will be less and the stiffness will be less, and as a result the deflection will be more. But when the depth is larger, second moment of area will be larger and the stiffness of beam will also be large, and as a result the deflection will be less. Moreover, if we want to reduce the deflection or we want to control the deflection, other than span, we can also change the end conditions. In case of simply supported beams, the bending moment at the center will be WL square over 8, and as a result the deflection will be large. But in case of fixed ended beam, the bending moment at the center will be WL square over 24. So in that case the deflection at the mid span will be less. So just by changing the end condition we can improve the stiffness, or we can reduce the deflection. So here it is a simply supported, so here the deflection is large, and in this case the beam, the ends are fixed, so the deflection will be less. So here we have a practical application how we can control the deflections. So there are some trees which grow their roots naturally when they feel that their branch is overloaded or the length of the branch is increased sufficiently and it will deflect. So they will grow the root just to change the end condition or to limit the span. So similarly here, to keep the deflection of this cantilever portion within the allowable limits, we can add this support. So this support will change the end condition, and as a result the bending moment will change and the deflection will reduce. Here again we have added some support, and here we also have added some support to limit the deflections. The last concept is buckling. So when a standard structural member is loaded with an increasing axial compression force, the member deflects laterally and fails by combined bending and compression rather than the direct compression. So this phenomena is termed as buckling. Under the application of axial compressive load, theoretically it should be failing in the compression. But if the length of the member is sufficient or sufficiently large, in that case, when we go on increasing the load, at one point the structural member will bend in the lateral direction and fail by the combined action of bending as well as compression. So this phenomena is termed as buckling, the lateral buckling of a axial compression member. So the critical load or the buckling load of a structure is load which creates the borderline between stable and unstable equilibrium. So if we apply the load in axial direction, so definitely it will deflect in the lateral direction, but up to a certain amount of load, when we remove the load, it will come back in its original position. But as we go on increasing the load, there will be a sudden increase in the deflection and the structure will fail and the structure will become unstable. So the load where the unstable equilibrium is achieved, so that is actually the critical load or the critical buckling load, or we can say a load where at which the buckling of the axial compression member occur is termed as critical buckling load. The buckling load of a column is proportional to the flexural rigidity, EI, and the inverse of column length, square. So it is proportional to EI and L square. So larger the flexural stiffness, larger will be the critical buckling load. It means our structural member will be able to resist higher load before the buckling, and smaller the length, larger will be the buckling load. So increasing the value of second moment of area of the section and reducing the effective length will increase the critical load. So here we have a demonstration for the buckling of the compression members. In this case we have pin end condition. Just with the application of load, it is bent in the lateral direction. So if we change the end condition, we make them fixed, here the buckling will be in this way and the effective length will be this one. And as a result, the load at which this buckling have occurred is larger. And if we provide some sun support at the intermediate position, in that case we can further enhance the buckling load. So in that case actually we have reduced the effective length. So when the effective length is less, the critical buckling load will be larger. So this figure shows the actual buckling of the bracing members. So under the application of compressive load, so these members have been buckled. So there is one other type of buckling which is termed as lateral torsional buckling. So this type of buckling occurs in the beam when a vertical load acts on the beam, so it suddenly fails or deflects in the lateral direction. So if we have a beam and apply a vertical load over here, so it will deflect in downward direction as well as in lateral direction. So this lateral buckling or the bending in lateral direction is termed as lateral torsional buckling. So if we want to improve the lateral torsional buckling, we need to improve its moment of inertia or the stiffness in the lateral direction. So to improve the stiffness in the lateral direction, if we increase the depth of the member, so it will not significantly affect the lateral torsional buckling. But if we increase the width of the member, so in that case, the second moment of area in the lateral direction will improve. For example, by increasing the depth, the moment of inertia about this vertical axis, about this y-axis will not significantly increase. But if we increase its width, in that case, the moment of inertia about this y-axis will increase significantly, and we can avoid the lateral torsional buckling. So we need to improve the stiffness about this vertical axis or the lateral direction. So to avoid or to protect the thin structural beams from the lateral torsional buckling, we can provide the bracings in the lateral direction. So lateral supports can be provided to prevent the lateral torsional buckling. So this is the pictorial evidence of support to resist the lateral buckling. The other type of buckling is local buckling. So if a structure buckles locally, so the buckling of this structure or this member at some point at locally, so it will cause the collapse of whole structure. So in case of tin peg or cane, drinks cane, so when we apply the load on it, so it will buckle at some local position, and then it will cause the complete collapse of the structure. So this type of buckling which occur at some point of the structure instead of the whole, it is termed as local buckling. So this figure shows the evidence of local buckling. So instead of this complete beam, the small portion of this section has been buckled. It has bent in the lateral direction. So such type of bending or buckling is termed as local buckling. So thank you very much. With this concept, we have finished our first chapter. In the next chapter, we will start the design of tension members.